Before I start the video, I would like to say that MathBusters is officially dead. Magic Mushroom has abandoned the project, and so yeah, this is no longer a MathBusters episode. This is just me randomly making math videos. I'll still make random math videos sometimes, but like, it's just not part of the series. So, yep. When you want the center of a circle, it's pretty simple because it's in the middle and you can use various methods to find it. To find the center of a square or a rectangle, you just have to find the diagonals and get their intersection. But today we're not talking about circles or rectangles or squares, we're talking about triangles, and not just an equilateral triangle, any triangle. What is the center of a triangle? It's such a simple shape, but there's tons of disagreement on what is the true center of a triangle. I'm just kidding. There isn't actually disagreement. The truth is that the center of the triangle can be whatever you want it to be. And so over the years, people have thought up of hundreds upon hundreds of triangle centers. So here's some of the most common ones that you'll see. First and foremost is the centroid. Now, I believe this is the most commonly used triangle center, as it is basically the center of mass of the triangle. Now, to find it, you simply have to find the intersection of the lines which connect each corner of the triangle to the midpoint of its opposite side, as shown in the diagram. Next is the circumcenter, which, appropriately named, is the center of the unique circle which passes through all three corners of the triangle. This point can be found at the intersection of the perpendicular bisectors of all three sides. Now is the orthocenter, which is the intersection of the altitudes of the triangle. The altitudes are the lines from the corners of the triangle that are perpendicular to the opposite side. And finally, there is the 9-point center. The 9-point center is the center of the 9-point circle. The 9-point circle passes through the midpoints of the sides, the feet of the altitudes, and the midpoint of the three corners and the orthocenter, hence its name. These four centers all lie on a line known as the Euler's line, which is really cool. Moving on to the incenter, which is the center of the incircle, which is tangent to all three sides. It is found at the intersection of the angle bisectors of the circle. Related to the incenter, there are three excenters. The excenters are similar to the incenters, but the circles are inscribed outside of the triangle instead of the inside. Although by definition they are not triangle centers, they are worth mentioning. This is the Nagel point. It is formed by the intersection of the three lines that connect each corner to where the opposite X circle touches the triangle. The incenter, the centroid, and the Nagel point form a line called the Nagel line. The Gergonne point is similar to the Nagel point, but for the incircle. It is found at the intersection of the lines from each corner to where the incircle touches the opposite side. This is the symmedian point. The symmedian point is the intersection of the symmedians of the triangle. Now, the symmedians are basically the medians, which are the centroid lines, which are reflected along their corresponding angle bisector. The Mittelpunkt, I don't know how to pronounce it, okay, I apologize, which is middle point in German, is a very weird point with many definitions. One of the definitions is that it is the center of the ellipse that is tangent to all three sides of the triangle while touching the X circles. But I don't know how to construct that in GeoGebra, and never will. But I do know that it is also equal to the intersection of the lines connecting these four centers. So they have that instead. Just speak here! The Spieker Center is the incenter of the medial triangle, with the medial triangle having the midpoints of each side of the original triangle as corners. Now, with this one, I really wish there was a more elegant way to describe this center, but unfortunately, there isn't one that works for every single triangle, so yeah. Die Feuerbach. Although the Feuerbach Point is, by definition, a triangle center, it's not what you would expect a triangle center to be. The Feuerbach Point is defined as the intersection of the incircle and the 9-point circle, and yes, they are tangent to each other. But because this point is on the incircle, it is always somewhere on the side of the triangle. In fact, it just refuses to exist when the triangle is equilateral, obviously because the two circles meet. So this is a special one. The Fermat Point is the point where the sum of the distances to the vertices of the triangle is its absolute minimum. Now, I wasn't able to construct this in GeoGebra because it's conditional. However, I can tell you the conditions. The conditions are that if any of the angles of the triangle exceed 120 degrees, then the Fermat point of the triangle is at that corner. However, if this is not the case, then the Fermat point is equivalent to the first isogonic center of the triangle. To construct the first isogonic center of the triangle, first you have to construct 3 equilateral triangles facing outwards on each side of the original triangle. Then, connect their apexes to the opposite corner of the original triangle, and their intersection will be the first isogonic center. The second isogonic center of the triangle is like the first, except the equilateral triangles face inwards instead of outwards. However, because facing inwards and outwards is also a conditional thing, I wasn't able to distinguish between those two in GeoGebra, so yeah. Notice how the angles between the lines from the Fermat point is always 120 degrees when it is the first isogonic center. That's quite interesting. Okay. I see you're tired of triangle centers. I mean, there's just so many, and I've explained so many to you, so what's the point of going on, right? But remember at the beginning of the video how I mentioned that the triangle center can be whatever you want? Well, it's true. Well, with one catch, and that catch is that the triangle center must be symmetrical. That is, no matter how much you swap the vertices around, the triangle center will stay the same. It won't bias towards one or the other. So, try this. Take any 2 of the aforementioned triangle centers and find their midpoint. Congratulations, you just made your own valid triangle center because it's still symmetrical. Or you could try and do what happened with the
Mittelpunkt.
Pick any 4 pre-existing centers, connect them together, and find the intersection. That's another valid center. You get the point. There are infinite valid triangle centers, however, only very few of them are interesting. However, people have become so interested in them that they created entire encyclopedias and books about these triangle centers, with an example being the Encyclopedia of Triangle Centers. So yeah, I think that's all I have to say about, well, triangle centers. I don't know, what am I doing with my life talking about these? But yeah, that's it. So, I hope you enjoyed the video. Okay.